Okay, here we are. I'm back. Limited capacity. We'll see how long I can talk here for. I also hate doing recorded lectures because obviously it's a lot different than being in front of all of you in the classroom and giving you the ability to make fun of me like you normally do. But so I think I'll be good here for 30 minutes or so. I also can't sit for very long, doctor's order. So we'll see how this goes. But with that, I wanted to start out by saying thank you for being flexible with me on this. I am available by email. I sent out my phone number. If you guys need to text me or whatever, I'll respond when I can. Don't feel like you're bothering me. I'll definitely let you know if you are. But as of right now, there's no homework posted. I'm planning to post a homework because I think you guys have everything you need to start it, and we'll probably have it due next week sometime. But anyway, to get back going, hopefully everyone had a nice spring break. Before spring break, if anybody remembers any of this, we started a note set titled Modeling and Discretizing, right? We've kind of transitioned away from everything you guys hated about this class, the theory, the background, how the finite element method is derived and how we utilize these field functions to create shape functions that allow us to determine the response to a system of elements based on nodal degrees of freedom. And that's really the basis of all this. And that's what is the foundation in a lot of the programs we use as structural engineers, a lot of the heavy analysis programs that we use. And we talked about that before spring break as well, some of the other options that are out there that not necessarily use finite elements, but help us out as structural engineers that are computer programs. And I wish I spent more time on it in some of the design classes, which maybe hopefully down the road, I'll be able to whittle in some time where we go through EnterCalc, and I can get you guys a student version of that because it is such a widely used tool that we use as a structural engineer. It'd be nice to kind of get you guys a little bit of experience in that world. But as we've been talking about model and discretizing for finite element analysis, right? What we are really trying to do is approximate the response of a real world problem, right? And I gave the example of our NaH, right? The fact that NaH is this very complicated, elaborate structure with all these different materials. And we are not going to model NaH directly, right? We're going to come up with a mathematical model, a very simplified version of this, which is really our structural model. But even still, the structural model itself is more detailed than we're going to end up modeling and getting answers for, right? I mean, some examples of which are like down on the far corner on the I guess it'd be the northwest corner, there's a stadium type seating down in the slab on grade. And as a designer in VA, we may or may not have even modeled that stadium style seating. And if you look at our VA model, there is no slab in our model anywhere, right? That would be right here, anywhere outside of where we have a basement area, right? So this is a basement for the NaH. And the reason why we modeled the basement is because it actually acted as a diaphragm. It was going to take load out of the moment frames that are framing down from above. That's these big columns here and here, right? And it's going to resist the lateral forces in those columns, pull the load out into the concrete floor diaphragm, and then extend it out into the tops of the concrete walls, right? And so again, at some point, we've got to make some decisions as a designer as where do we start and stop? And then I've talked about it multiple times with you all already is, it's up to you as a designer. It kind of really depends on what are you going after for the results, right? If you're worried about the force in the column way over here, say on the right-hand side or the west end of the building, you don't necessarily care how well you model or discretize or break up the floor slab, or if you model even the foundation wall, because that's what all these pins are here, is modeling the top of the foundation wall for the full basement. And so it depends on what we want is going to dictate how we're going to model this. One of the bigger reasons why we modeled the entire building here in NaH is because we did a modal analysis on the structure because it had some irregularities. It also, one big thing you'll find from architects is they like this idea of the story of the building. And I know it's a really kind of soft aspect of design, very very creative way to look at it. But you'll hear it in industry talked about when a designer goes to design a building. They start talking about, well, what's the story of this building? What was the catalyst for why the money came about to build this building? Who are the users of this building? And ultimately, for generations, what is it going to be used for? And that's all part of the story of the building. And because this building was an engineering building, they really liked the idea that we were using, for those of you who have taken Mike's 512 class, using a higher order seismic analysis method to then come up with the design demands in our structure. The hard part about that is, it adds to the story, but it also adds to the complexity of the design. One thing it does allow the architects to do, for those of you who've taken Mike's class already, is it gives the designer flexibility. So we get all these weird angles. I mean, there's no square. There isn't a whole lot of square angles in Norm. It's kind of has this real shallow angled front and back face. So this face here and the back face back here, they actually are not parallel to one another, which obviously added to some complexity. You can really see it here in the clear story, where the difference in the depth of the clear story is that at the west end, and at the east end it opens up a little bit. And so obviously some complexities for us, but also, as I mentioned, I guess getting back to the finite elements, all of these things play a role in how much of this building we design and how intricate and how detailed we get in designing it. And so if we go back here, we really have to boil down our, incomplete building and come up with this approximate mathematical model that we're going to try and represent in our FEA, our finite element analysis. So we need to take the real world and develop the mathematical model. We want to capture behavior of interest to an acceptable level of accuracy without making model too complicated, right? And I just kind of went through that. We need to do that by simplifying a lot of things, right? And these are all at the discretion of you, the designer, right? The engineer. And when I say, you get to make these decisions. You don't just get to make them and say, hey, I have based on PE number 52,003, I'm going to do this, right? You have to have something that's defendable. And if there's some of the few things to take away out of any of my classes, I would say making sure that the decisions you make as a designer is that you can defend those decisions. And those decisions can be defended based on a lot of things, and a lot of what the code is there, as much as we gripe about it and they're really big and all the materials we have to deal with, that is a very defendable piece of resource for us as a designer to say, well, why are you doing it this way? Well, I'm doing it this way because ASCE 7 tells me that we need to consider this, right? And so those are defendable aspects of making decisions. And so we simplify loading. We might take story shear from the earthquake or the wind and apply it as a point load in the diaphragm, a pressure on the wall, or a line load on the edge diaphragm, right? There's a lot of different ways we could load our building to get the same shear forces within it. It's just going to change the load path, and that load path is going to change, which is going to change our results in some cases. But it might not change the accuracy of our analysis, because we might be looking at something that it's okay if we just apply a diaphragm point load as our base shear at each level, versus putting a line load on the side. We talked about that last week a little bit. Also, modeling self-weight versus considering just load magnitudes. There's just some simplifications there. Self-weight, as we know now, we have these things called energy equivalent forces that we apply at each of the nodes. And so our finite element analysis software is going to take all of our self-weight, and that self-weight is going to be, provided as loads at our nodes, right? Because it's really just a uniform load based on our gravity direction. And it's going to have to run through the analysis to put it at the load. So we can simplify things by saying everything is weightless and apply load magnitudes, or apply loads either ignoring the self-weight based on those load magnitudes or including it. We also think about materials based on linearity versus nonlinearity, homogeneity, anisotropic versus isotropic. So, how uniform is the material? Does it behave differently in the two coordinate directions? There's also differences in shapes, right? Composite shapes versus assemblies. Can we take, and I showed you the, shape builder is a very helpful tool that VA produces to analyze shapes or cross sections. And you can import those actual shapes and cross sections into VA, but is it worth it to do that? Sometimes it might be worth it to do that. Maybe you are going to be very specific as to how to model things. Maybe if you are doing glazing in a big high-rise building, you'd want to have those specific cross sections in VA. In other instances, maybe you just are curious into the stiffness, because I'm not really worried about the intricate, micro scale of what's going on where a mullion in a window hits a cross mullion in a window or a sill in a window. We're really worried about, well, after the wind hits this whole curtain wall, how is it going to distribute that load? Well, it's going to distribute it based on stiffness, so I'm just worried about the cross-sectional properties. We also simplify stress behavior a lot of times. Even though our concrete floors are technically acting as two-way regardless, we have this dominant stress direction or strength direction, which allows us to assume these one-way behaviors, which in reality, it probably behaves one way, maybe out in the middle of the span, right? So the aspect ratio greater than or equal to 2 gives us a one-way span direction. And we normally have two-way regardless, but we can make some of those simplifications. Plane stress or membrane, right? Do we have through thickness shears going on? Do we have bending in our plates? And do we need to worry about our plates and bending? We also want to simplify boundary interelement connectivity. Foundations is a huge one. I talked about that last week. Pinned versus fixed versus the code allows us to model the soil interaction. I think that would be a huge guess from at least my understanding of geotechnical engineering. I'm sure there's products out there that allow us to do that. I'm sure there's plenty of buildings that get built that way, but I'm sure they're very large scale buildings where maybe there'd be some economy to spending that much money on interaction. A lot of times we make the two very approximate or approximations that our foundations are either pinned or fixed, right? We have boundary conditions at beam to beam and beam to columns, right? Those simple connections are fully restrained moment connections. We have diaphragms to beam to column connections. We have to worry about that. If we're trying to interconnect beams to diaphragm, we want to make sure that our elements are interconnected at nodes, because that's the only place that elements know that each other exists, are at nodes, right? Not between them. As I mentioned, there's many simplifications. There's common ones for most. Pin versus fixed foundation, homogeneous material, it's consistent throughout. Pin connected elements, right? We have member releases where we have simple supports, and then diaphragm stiffness. A lot of times we have to model this very large flat plate that's our floor system. It's a very in-plane stiffness element. A lot of times we assume that thing acts as a membrane element because we're not really worried about designing it in our finite element analysis software as a bending element, unless maybe it's a concrete building and you have a full slab like Cobley Hall or something like that. But for concrete on metal deck, we usually are going to design that, as some of you have been in masonry now have figured out, designing pan deck or concrete on metal deck is tableized. So you go out to a manufacturer's table and you pull out prescriptive allowable load values. And so you can do that analysis out on the side, and then you really are just worried about modeling the stiffness of the diaphragm. Not necessarily its out of plane stiffness, but its in plane stiffness becomes the important part. So we use our mathematical model as a framework for development of the finite element model. When we go to select elements, we need to decide. We make right. We need to match the element with the desired output or intent, right? And we've talked about this already today and last week. What are we trying to get out of this model, right? Are we worried about the base shears at the bottom of this model, or are we worried about the beam to column moment shear and axial demands in a moment frame? Or are we worried about the in-plane shear and the diaphragm at the second story level adjacent to the elevator, right? Or something like that. And so we need to match the element with the desired output or intent. So that would say, are we worried about a plate element versus an area. Okay. So some of you earlier on in the class, I opened up VA. We kind of navigated it really briefly. But there's two, I guess I would say, plate elements, but they're really not. There's one plate element in VA, and that is plates. So if you go and you go to draw a plate in VA, you're going to pull out that almond triangle, right? Or the almond triangle with the zoo triangle added onto it. And so that plate element that you're drawing, whether it's membrane or a thick, thin plate, adding in those additional degrees of freedom that we talked about. If you're modeling it as a plate, you're really interested in what's going on in the diaphragm or in that plate element. Shear wall, for instance, you could model like that. And you're worried about what the bending stresses are, the in-plane stresses are, strains or displacements, right? If you're worried about what's going on in that plate element, whether it's the diaphragm or the roof sheathing or the wall sheathing in a shear wall or the concrete in a concrete shear wall or something like that, then you're going to want a element that's going to give you the demands. An area, okay? An area is not a finite element, okay? I'll say that again. An area is not a finite element. I know this gets confused every time I taught this class. It gets confused just in other classes. And so I'm trying to make it as clear as possible here. An area, the ability to draw an area in VA, the area only gives you a means of distributing load. So an area is VA's way of giving you a quick and easy method of, if you were designing Cobley Hall, and you were going to draw an area for the floor, second floor of Cobley Hall, right? Tate Lab. Tate Lab requires a uniform live load of, say, 60 pounds per square foot or something close to that, I assume. And then the design architect comes to you and says, oh, well, by the way, we're going to put Tate Lab actually on the other end next to the CE office. And we're going to take all those offices on that end and the geotech lab, we're going to flip it over and we're going to put it on the other end. Right? And that's going to change up all of your uniform loads throughout that second floor of Cobley Hall. Well, if you modeled it as a plate, you'd have to go through and you'd have to move all of those loads off of all of those plates that you decided. An area is nice because an area just allows us, we can load our area, and then that area distributes that load to supporting elements, whether it's beams or plates. And so the area is nice in VA because it gives us this quick, easy method of distributing the loads to our supporting element. An area has no stiffness whatsoever. So if you just drew Cobley Hall, right, with its columns, big wide flange columns that are encased in concrete, and then you put in these areas that represent the floor in Cobley Hall, right, the floor has zero stiffness. That it would not have any in-plane or out-of-plane stiffness at all. You couldn't, if you loaded those areas and you didn't put anything underneath that, like a beam, a girder, or a plate of some sort, it's going to have nowhere for that load to land. And it would probably distribute it back to the columns. And so an area is really powerful because it gives you this ability to spread loads to supporting elements, which allows you to change the beam configuration below an area, and it's going to automatically change how the loads are distributed. And you can decide whether the load gets distributed as a one-way load or a two-way load. Even more helpful in VA is now you can draw an area, and then you can then take that area, and I think some of you did that in the first homework assignment, right? You draw an area and then you can mesh it into plates, right? But until you mesh it, it has zero stiffness, in plane or out of plane. And so once you mesh it, then you can give it a thickness, you give it a material, right? Those are going to give it some of the cross-sectional properties as part of our stiffness, right? As our almond triangle or our zoo triangle. And so areas are increasingly becoming the better choice or the preferred choice to design diaphragms or in-plane elements because it also allows us to auto-mesh things. And auto-meshing is incredibly valuable because we can change the mesh quantity, which allows us to check convergence easily without making sure that all of these interconnected nodes match up to interconnected elements, right? We have a vertical wall and a horizontal diaphragm, right? We need to make sure that that wall and the diaphragm are connected at nodes. And so VA will do that internally, and you can see it in its meshed configuration in the results tab. And so plates versus areas is one thing. right? Do we do plates versus a beam, right? Or do we have beam behavior, or do we have plate behavior for our element? And we have membrane versus bending. Are we worried about our shear wall taking out of plane loads, or can we just model it as a membrane element, right? I think it just depends on that shear wall configuration and the building design and things like that. If it was a shear wall that took exterior wind pressures, then I would say yes, probably want it to be a bending and membrane element. But if it's an interior shear wall and maybe it stops at the ground floor, there really isn't much internal pressures applied to the outside or to the sides of that wall. Maybe you could get away with just assuming it's a membrane element. That's going to be the dominating demand on that element anyway. So discretizing, right? Now we're gonna break everything up. This is a really big deal. This is where you got to put some thought into it. One, because depending on what you decide, the number of elements, we might just say, and some of you did on the first homework, we're just going to use the maximum amount of elements I can possibly use because I'm limited by the educational version. Can you do that? I guess you probably can do that. But I would also like, and as we continue to actually model some projects here, that I want you to do a analysis when you run your model, or when you're developing your model. Run a convergence analysis, right? And to do that, we need to adjust the discretization of our elements. And so when we look at discretizing beams and columns, we really are interested in, we need to capture connectivity and compatibility. In other words, we need to make sure we provide adequate load path. Right? So typical applications, and we've seen this, and I know a lot of you have modeled in VA or other programs, typically, in typical applications, pain pills and me do not get along very well. They get really fuzzy. So typical applications only require one element per mathematical model member. Okay, so typical applications only require one element per mathematical model or mathematical model member. Why is that? Well, because when we look back at our beam element and we look at beams and columns, we pretty much capture, for the most part, our displacement function, as we know, is a cubic in those elements. And so it doesn't necessarily come up with the exact answer unless we have a uniform load between our two nodes that is equal to zero, or transverse load is equal to zero. But, I mean, it's pretty close, a cubic versus a fourth order, fifth order polynomial. We're going to get really close to the displacements between our member elements. And so there are some special cases where we would want to consider maybe breaking these elements up even more, right? One of them is adequate load path, right? If we want to create adequate load path. So I'd say diaphragms, and also we talked about this, P delta and P little delta are some examples of special cases where we're going to want to make sure that our beams or our columns are broken up, right? A good example of this would be like if we had a shear wall, and I guess let's make it a really cool shear wall. We'll make it a special steel plate shear wall. So in a special steel plate shear wall, we end up with beams and columns that bound a steel plate, right? So we've all seen concrete shear walls before, maybe masonry shear walls, wood shear walls, right? It's just some sort of thin in-plane element that carries the shear, right? So steel plate shear walls, special steel plate shear walls are the same thing. I think they're badass. No one ever really uses them, honestly, but I wish we got to use them more. But all it is a member or a steel plate that's bounded on all four sides by some, what we call a boundary element, usually a beam or a column. Well, if I modeled, this is a column, this is a beam, maybe these continue down, and we have another steel plate shear wall below, right? And a steel plate shear wall above. This is our story level. So we got these beams that continue framing on, right? If I modeled this in VA and I modeled the steel plate, right? And I modeled this as a single plate. Well, it's not going to allow for the distribution of forces, right, along the entire length of the edge of our shear wall, right? If all we have is nodes at our four corners, that's the only place in which our elements know each other exist, the beams and the columns, right? And the beams and the columns and the plate. And so in reality, we've got this connectivity between the plate and the boundary elements, the columns and the beams, right? Largely, it's either bolted, and it's a big series of bolts, or welds. And so we would then, create or want to break up our model to better represent that connectivity. And if you modeled this steel plate shear wall as an area in VA and then meshed it, there's some auto meshing features in VA that in order for VA to get some of the internal results that you see in shear and moment diagrams and things like that, they actually break up the member into smaller elements and run analysis within them in order to get some of those intermediate results. And so it's already kind of internally breaking up these beams and columns. And so we end up VA uses that and it knows where it breaks them up. And so it'll interconnect that, and you'll see it with these nodes that are kind of, shaded out. And so that's one typical application. So for a shear wall or a diaphragm, same thing. If we looked at this and now we're looking at beams and girders and we're looking at the floor level, same thing. We would want to make sure that we can drag load and distribute load in and out of that horizontal load element, the diaphragm, based on all of these nodes, right? Instead of just having the four corners. Another example is our P delta, which we've talked about multiple times now, right? If we had a column and it had axial load on it, it's going to deflect something like that. That's not even really right, but it's going to deflect something like that, right? If we had a force on this cantilever, right? A vertical and horizontal force on this cantilever. The horizontal force is going to create a displacement, and then that vertical force now all of a sudden is going to be based at some small amount of delta, right? Big delta. And then on top of that, this element, this cantilever, it may deflect between the ends of the cantilever to the top of the cantilever to the bottom of the cantilever. Now all of a sudden we have another displacement within here, right? That's P little delta. Well, we're going to capture P big delta in our analysis because we're worried about, right, that nodes ending or moving through our system. So we've got a node here and a node here, right? 1 and 2. Well, as node 2 moves over, right, we know where node 2 is relative to node 1, and we talked about this geometric stiffness matrix and things like that. The VA mobilizes to analyze the stability of this system. But the P little delta is going to get lost, right? So in order to incorporate P little delta, we need to break this beam up or column into smaller elements so that it can actually know where it is, right? What the displacement is that P little delta is along our overall length of our element, right? So it's really doing a P big delta analysis, but does it at the small level where then we are able to capture P little delta. So those are a couple instances where you would be, it would benefit you to look at them in that regard. So, I can't remember when I started. I think I'm like halfway in, or 30 minutes in maybe. So, walls, floors, and foundations, right, relative to discretizing, right? Well, walls, floors, and foundations typically are very indeterminate. So I would say indeterminacy of elements require extra thought on layout, right? Stiffness attracts loads. So depending on how we discretize things, right, we're going to affect how load is transferred throughout the system and where the stiffnesses are located. You can imagine if you had one big one element for the entire floor level, that's going to be a bit stiffer than it will be if we were to break that one floor level of Cobley Hall into 10,000 elements, right? We can, unfortunately, with these, especially with indeterminate elements, walls, floors, foundations, things that we're dealing with, plates, right? We can easily start to overwhelm our analysis software. So overwhelm software. In pursuit of an accurate model. So what do we do? Well, we start simple. And I've mentioned this before. I think Adam mentioned it when he came into class, right? We start simple. Why do we start simple? It's because we can, at some level, right? At some simple level, we should be able to validate our answers. Right? We should, at a simple level, be able to understand the behavior and the load path and what's going on between elements, right? And so if you know, we're going to design a, say, norm, for instance, it has all of these off angles, nothing square, it has clear stories, it has these, you know, vertical offsets, horizontal offsets in the lateral resisting system. It's a big moment frame, right, which is complicated in its fully restrained moment connections and things like that. I mentioned you have to take the stiffness of those connections into account, which proprietary businesses that design those such elements are able to help you do that. But you have to integrate it into a model. So what do? Well, you start with something very, very simple. Like I like the fact that the stairwell, the enclosed stairwell in the parking garage to the south of norm, right, and connected to norm, that's really a very, very simple structure, right? It's got 2 or 3 bays in one direction, a single bay in the other direction. It has brace frames in one direction and moment frames in the other direction. And so very simple systems, very consistent diaphragm layout. And you might even try and start even simpler than that and load it up and make sure that, you know, boundary conditions are giving you the results you want and the behavior that you would expect out of it, whether it's the displacement, whether you'd get some torsion out of things. At some capacity, if it was very simple, maybe a 1x1 box, and in one direction you had moment frames, the other direction brace frames, you could probably calculate what the displacements are at certain levels based on mechanics, right? Axially loaded truss in one direction versus bending in the other with moment frames. And so you can start very simple and step into the complexity because in order to get convergence and discretize your model appropriately to make sure you're getting the accuracy, in quotes there, that you want out of your model, right, you're going to have to add some complexity and add computational requirements for your software, which is going to very quickly overpower any software package now. Is not that hard to overpower. I mean, if you're doing simple things, yeah, but if you're doing, say, norm, I mean, that's not a very big building, right? And so it would take hours to run that model. And so you got to have to try and think about, accuracy and acceptable accuracy versus the amount of runtime. So refinement ends up being or becomes a large part of discretizing. Right, so you don't have to have the same mesh count for every plate within your entire building, right? So like in Norm, for instance, there are some areas of that building which are kind of out in the middle, right? And we're not too worried about what's going on out in the middle relative to force transfer and things like that. So maybe we can handle a coarser mesh out there. Maybe our plates are, 10 square feet. But then as we get closer to these moment frames, maybe we get down to half a square foot, where we interface between vertical lateral resisting elements and horizontal lateral resisting elements, right? So our shear walls are moment frames to our diaphragms, our roof elements, right? So this gives us, or we then require more focus on load path and results of interest which leads to more plates, like I mentioned, at some of those locations where we have intersecting elements, right? So at connections to other elements, at load sources or supports, at discontinuities, right? An element ends vertically as it extends up the building, things like that. Load sources is another big one, right? If you put a point load at the center of your diaphragm and say it's 100 kips, right? You're applying that as I've explained at a node, and that node represents like the tip of a ballpoint pin, right? I mean, it is tiny. It is a specific point within that diaphragm. And so you imagine the real world if you were to do that. I mean, you're going to have huge stress concentrations sitting right there. So there's this idea of, well, if we're going to have this applied load, do we spread it out over multiple nodes, right? And create maybe we create 100 elements that represent the boundary or beyond the boundary of a base plate of a column that's deciding that it wants to land on our floor, right? And then we apply a pressure onto those plates instead of discrete point loads at the nodes of those plates, right? All of those things are going to help us to distribute that load prior to now having to distribute it throughout our elements, right? Because otherwise we're going to get to these huge spikes, and we'll see it later on when we start modeling plate elements. All right. I think this is the right one. Nope. Nope. Sorry. About ready to have to stand up here. Okay, we're gonna get through this. Part 2, documentation. This part to me is super important, right? So as I mentioned, right, we want to make sure that whatever decisions we make as a designer, that they are defendable, right? We could go to, in some cases, maybe a jury, or one of your fellow engineers, or maybe one of your peers in the market that you work in. Maybe it's, I work at Morrison Merrily, and Neve works at IMEG, and Neve, all of a sudden, the client came to Neve and said, yo, I think Tim's, messing with me here, and we're spending way too much money on this building because he's over designing the whole thing because he's scared. And so Neve needs to step in and he needs to look through my analysis. And he's going to have a better chance of understanding what I was doing if I give him the tools to understand the software that I used, the assumptions I made, right? Some of those very early on assumptions that boils down our real world problem to our mathematical model, right? Some of those things relative to supports. Do we assume pinned versus fixed? Relative to materials, right? Do we have anisotropic or do we have isotropic materials? Are they homogeneous, right? All of those things, right? And so it is very, very important. And I think it's funny because I don't think this happens very often. And I don't know if it's a generational thing, but I definitely had comments after I taught this class the first time that the second go around, or that those individuals, they go out and they start working in industry, right? And their supervisors were surprised, and I think it was a good surprise as to how documented they were when it came up to developing their finite element model. And so I think it's a very good thing. I expect you to do it in class when I assign this next homework. I expect you to just have a little sheet, and I can walk through. I'll probably walk through next time on Wednesday in the notes. Walk through an example of what that description looks like, right? Things you talk about, what you might include in it and things like that. It doesn't have to be a novel. It just has to convey, what your methodology was for developing the model that you have, right? And our documentation that we make in all of our cases, and our big documentation for us is our calculations, which includes our model, and our drawings, right? Ultimately, the drawings are what's conveying what actually gets built. And so in order to transfer that knowledge, documentation is key to either mitigate litigation, right, or defend against it. Hopefully no one ever has to do that. I have not, thankfully. Maybe during design, right? This happens all the time. All of you have worked as interns, right? You go out and you work in the real world for a summer or a winter break or something like that. And then all of a sudden you're gone, right? So, and I had interns. It was great. I have them during the summer. Towards the end of the summer, I made it a very apparent request that I would like them to go back through anything that they're working on the last week that they're working and describe what they've done, how they did it, in order to help transfer, right? Because when they're gone, I'm going to have to go through their paperwork. And so they need to make sure that their documentation was enough to where I can understand what they were doing. We've had projects where we retrofit or do renovations or got future work or future projects based on the fact that we did the first project, right? The scoreboard that's going up in front of the big scoreboard, by the way, 100 feet wide. Scoreboard that's going up at the stadium right now, that was a more summarily project, right? We did the original scoreboard. Well, so what makes more sense than to have the original designer? So when Montana State decided to go for this huge, Jumbotron thing that they're putting up now, they likely went to the original drawings and said, oh, here's Morris and Mary, let's call them, right? We have all the original drawings. We have hopefully all the original analyses that we did and modeling that we did. And it gives all of us a leg up. And hopefully whoever did the calculations for that, it wasn't me, I think it was Brian Ashton. Hopefully Brian was methodical in his, note-taking and his calculations in order to, make it apparent as to why they were sized, the current piers were sized the way they were, and whether or not they can use them. And it looks like they could use the existing one, which is very nice, right? Also helps in construction administration. Right? We're not done yet as a designer when we are completed with our calculations and when we're completed with our drawings and we send them out the door for permit, right? It depends on the project, but I would say 99% of the time, if it's a commercial project, usually you're involved to some capacity as a designer during construction because ultimately everyone makes mistakes. Contractors make mistakes in the field when they go to build it, and we as a designer make mistakes, right? Architect, engineers, mechanical, electrical, plumbing, right? Everyone, civils, everyone makes mistakes. And so during the construction phase, sometimes we have to work around some of those mistakes and improvise. And so having some documentation as to, well, what was the unity value for this connection? And what did we assume for the stiffness that made this happen and things like that? It allows us to continue to move forward. Another big one, which I think forces a lot of consultants to be very meticulous in their documentation, is when we do third-party review. And I would say every building on Bozeman's campus gets reviewed not only by the city of Bozeman, but then they take all the drawings and the calculations, they send it off to a third-party review firm out in California, which is called ESCIL. And they are methodical. They go through, and what ends up happening is at the end of that review, we get back a little kind of tallied sheet of all the notes, and they're very specific. They'll say, "Hey, ASCE 7, chapter 12.8.4, talking about shear design or seismic demands and things like that. You didn't consider this, and the code says you need to consider this. Explain how you considered it." Right? So you got to go back through calculations and justify that. It gets kind of weird when you have to provide more documentation, right? Because that kind of gives ESCIL the idea that, oh, well, maybe they didn't even consider it. And that happens too, though, right? We're all humans. We make mistakes and some things get missed. And so third-party review, in my opinion, is a real good motivator as a consultant to make sure you're crossing your T's and dotting your I's. So we'll talk about on Wednesday more about what's included in this documentation, the description and the intent of the model and things like that, and we'll keep moving forward. Again, if you have any questions, I'll post this on YouTube. I'll send a link out to D2L, and I'll continue that kind of method as we move forward. I am truly hoping that I will be back next week in class. I'm just very limited in my abilities to be on my feet for an extended period of time and or sitting. I'm kind of stuck in the middle. Anyway, we'll talk soon. If you have any questions, email me, call or text.